So hey everyone, my name is Robin Brown and I'm a PhD student in the Stanford Autonomous Systems Lab. Today I'll be presenting some of my work on solving co-positive optimization using Ising solvers. And this work is in collaboration with a number of my wonderful colleagues at the NASA Quantum AI Lab, as well as at Stanford as well. In the past few years, there's been a lot of excitement about the prospects of quantum computing. So unlike Shor's algorithm and some of these more tailored algorithms for solving very specific problems, we're starting to see more general frameworks for using quantum computing. And one framework that has emerged is the problem of solving Ising problems. So the problem with solving Ising problems is the problem of finding the ground state of a discrete quadratic minimization problem like I have on the slide here. And due to the wide variety of technologies that implement this problem, this has inspired a lot of research into trying to understand how to incorporate these Ising problems into the solution process of difficult optimization problems. And one standard approach that has emerged is one where you really take your problem and force it into the Ising form. So that typically involves discretizing any continuous variables and moving your constraints into the objective using a penalty function. However, a lot of these near-term quantum devices are just heuristics. So what this means is that while they might return good quality solutions to the Ising problem, there's no guarantee that the global optimum is returned. And they have really struggled to characterize what the optimality gap is on the return solution as well. Now, for me, we were looking at applying Ising solvers to problems and verifying safety in robotic systems. And that's the setting that we really need guarantees on optimality. So that motivated us to ask the question of whether it was possible to convert black box and heuristic solutions from these Ising solvers to ones with rigorous optimality guarantees. And we wanted to do so without losing quantum advantage. And I'm here because the answer to the question is yes. And I'm going to tell you in what settings we can do this. So in our work, we consider mixed binary quadratic programming problems. And this is characterized by a potentially non-convex quadratic objective, linear equality constraints, non-negativity constraints on the variables, and some of these variables may be binary. And for me, this is exciting because this framework generalizes model predictive control and neural network verification, which are applications that are near and dear to my heart. And I think that this should be exciting for this audience because this also generalizes many NP-hard problems such as maximum fleet and scheduling and routing. And the meat of our approach relies on the fact that there is an exact convex reformulation of these problems. So what we do is we generalize a result of, or we extend the result of Samuel Beer in 2009, where he showed that there is an exact convex reformulation of these problems as completely positive programs. And the dual of these problems is a co-positive program. And what we're able to show is that under feasibility and bounded feasible region of the original problem, there is no duality gap between these two problems. And it's not too important to parse all the math that's on the slides here. It's really routine and formulaic transformations to go from the original problem to this problem. So I've highlighted them in the corresponding colors to see how that transformation works. And now I know what you're thinking. If you have an exact convex reformulation, does that mean the problem is easy? Does that mean the problem is solved? And the answer is, of course not. I would be having a different conversation if that made the problem easy. What we gain from this approach is that this convex reformulation really packages the complexity of the problem into the co-positivity constraint. So examining this co-positive program a little bit further, we see it has a linear objective and it has a constraint on a linear combination of the constraint matrices. And this linear combination needs to belong to the cone of co-positive matrices, which is a convex cone. The catch here is that checking membership in this cone is co-NP complete, so that's not easy. However, checking co-positivity can be posed as a non-convex quadratic minimization problem. And this should start to ring some bells because Ising solvers can solve quadratic minimization problems really well. So we start to see that there's a very natural synergy between solving Ising problems and checking co-positivity of a matrix. And if a matrix is not copositive, then this optimal solution will be negative, and any negative solution to that can be used to construct a feasibility cut, separating that configuration of variables from the feasible set of variables. So now that we have this formulation in hand, what we're going to do is solve this problem using cutting plane algorithms. And I have a star here to remind myself that I need to qualify what I mean about cutting plane algorithms for this audience. When I refer to cutting plane algorithms, I refer specifically to cutting plane algorithms for solving convex optimization. And it's similar in flavor, but not quite the same as the cutting plane algorithms that we see in mixed integer optimization. They're also referred to as localization algorithms. So the way that a cutting plane algorithm works is that you maintain an outer approximation of your optimal solution set. The algorithm generates a test point, and you add a separating hyperplane, or you add a feasibility cut that reduces that search space, and then you update your outer approximation. And the intuition for the way that this works is that if you very carefully choose your test points to be some sort of center of your outer approximation, then you can ensure that you're making consistent progress in reducing the size of your search space. So the picture that you should have in your head is this is high dimensional binary search. It's just a little bit more complicated in higher dimensions. And what we're going to do is that we're going to check copositivity using the Ising solver and carry out everything else using the classical computer. And what does this get us? So I motivated this talk by saying that these near-term quantum Ising solvers are just heuristics, right? So we want to make sure our algorithm is tolerant of the fact that it's heuristic and can really take that into account. So when we make our copositivity checks using an Ising problem, any configuration of those variables that results in a negative objective can be used to construct a feasibility cut. While the global optimum will give the deepest cut, any negative value is sufficient and doesn't mess up our convergence guarantees. So that kind of buys us resilience to the fact that we may or may not have the true ground state here. And I mentioned convergence guarantees. There's a wide variety of different cutting plane algorithms. They vary in the resolution with which you maintain your outer approximation, the amount of effort it takes to compute the center. But one key feature of all of these algorithms, except for this center of gravity algorithm, is that they take polynomial time in computing the center in terms of the number of variables of the problem, and they are guaranteed to have a polynomial time in the number of outer iterations. So when we put this all together, we see that the part of the algorithm that the classical solver is handling is guaranteed to be polynomial time. And I think this is really interesting because what this suggests is that if we apply this algorithm to exponentially hard problems, the complexity of that problem is shifted onto the Ising solver. Now, if these Ising solvers can give us an exponential speedup, and that's an open question that the physicists are still trying to figure out, but if that exponential speedup is there, we're ready to take advantage of it, all without a proof or without experimental validation of that speedup. I think I'm out of time, so I will conclude that there, and I'd be happy to take any questions.
So I didn't get it. If you don't get a negative objective function,
Yes.
it doesn't mean that one doesn't exist, right?
Yeah.
So how does your convergence work with that?
Yeah, so there's different ways that you might want to handle that, and that's where you kind of get a little bit heuristic-y, or you have to make decisions based on the Ising solver at hand. But if you have a lot of like small objective value, but not necessarily negative objective values, you can still add a cut that doesn't necessarily cut off that point. So they're referred to as shallow cuts. And that ensures that you're not making any mistakes in your solution process, but then you might lose out on some of the guarantees there, right? But that they don't tend to, if you only have like a couple in your solution process, that doesn't tend to derail your solution. Or another option is to assume that your Ising solver is right and keep track of what assumptions you have made, and then you can backtrack if it says that there's no feasible regions left.
All right, that's